is that one all the way down to the last line. So if you can't see the bottom of that, you might want to move sideways, or if it's really bad, I can shrink it a little bit.
Stuart, I have a couple questions.
Sure.
One is, will we actually need the internet at all during this session?
You will not.
Okay.
You might want it. You might want it for...
That's fair. I was just thinking like turning off all the screens.
Sure.
The other is there any reason why you would advise us to use the regular REPL and not something like IPython?
Doesn't matter.
Okay, thanks.
Is that totally true? You'll see subtle differences in some of the built-ins probably. Other than that, no. What editor, whatever. You can use whatever you want. Like what you will need to do is type in some things into the prompt. But which prompt doesn't matter to me. Is there another plug up here? Somewhere obvious? Yeah, I'll trip over it when I go along the left side. 1, 2, 3, 4. T minus 3 minutes. Me what? Oh, do you want an electronic copy, you mean? Or like everyone should have a copy of the handout.
Where do we go?
The tutorial assistant in the back was handing them out as you came in. Just didn't hand it out to you as you came in. So everyone should have a handout. If you don't have a laptop, which happens every once in a while, then convince your neighbor to let you look over their shoulder. Python 2, 7 or higher is fine. Python 3 is fine. Open up your prompt and be ready to type a few things. There's a bottleneck at the back. While we're waiting, let me ask you a few questions to get to know you. How many of you are using, that's a silly question. I was going to say how many of you are using Mac, I can see. Because they've got these little funny shaped lights on the front. Just kidding. How many people are using Python 2.7? Python 3? Okay. There'll be a few differences in what you see, but everything you type should work just fine. I've tested it in both. Although I have made a few changes since then. I'm actually still running 2.7, shame on me. How many of you are, what distributions are you running? Just probably doesn't matter. I mean, what distributions are there on Mac? And I know what there's on Linux. I know what there's on Windows. I don't know Mac very well. Not a helpful question. Anyone running IronPython? Jython? No? Okay. Anyone running PyPy? How many of you came from another programming language? And of those, how many of much of your work was done in a C++, Java, static compiled world? Okay. How many of you have used Python for less than a year? Less than 2 years. Less than 3 years. Less than 4 years. More than 4 years. Okay, cool. And is there not enough seats? There's one right here. I see an empty one there, an empty one there. Yep, it's been a common problem. This morning, there were some people that actually walked out and got their refund because they didn't realize there were some chairs that were stuck in the corner. And again, 6 people on one table is pretty narrow, so it's understandable. So that was and I think in that one there were some chairs missing as part of the problem. So that one, on top of that, there were chairs missing. But okay, I think we're ready to get started. AV crew, you ready? Ready for me to go? All right. Well, welcome everyone to the Python Epiphanies tutorial for PyCon 2014. I want to start by explaining what I'm trying to do here. As you will have read in the description of the tutorial, my target audience for whom I developed this tutorial, I started with the audience first and said, what do these people need? Is people who had been using Python for a number of years, a few years, often coming from other languages, and found that their level of Python expertise was sort of going up, and then it plateaued a little bit, and they were getting confused and frustrated sometimes. And I'm going to try to help you over that hump, those of you who are there. And we're going to look behind the scenes or under the hood quite a bit to see how Python does some things, and that I hope will help you understand what it's doing better. And then some of the questions you might have will be you'll be able to answer yourself instead of, if you ask, was Python passed by reference or passed by value? Well, when we get to that part, I'll let you answer it because of the other stuff we'll build up to. You'll go, well, of course it must be one of those. Well, actually, neither of those. As you see, these handouts are really important. You're going to be doing a lot of typing from these handouts, and I have not given them to you in electronic copy because I want you to type and actually write the stuff down. I've tried to make it short identifiers and commonality from one line to the next so you can hit up arrow and make a small change, because I don't want to frustrate you with your typing, but I do want it to be going through your fingers and make your brain work to think about that. Question? No, they're in the back. I don't think you will find any typos in here. So when you hit the first error, it means I put it there on purpose, right? So what I want you to do is when I ask you, do an exercise and you type in a line, before you hit enter, look at it and say, what is that going to do in Python? And then when you hit enter, if it does something different, that's an opportunity for you to learn something, including the cases where I've injected errors because I want you to see how things are failing. About 500 lines of code, lots of one-liners. Fortunately, I won't be typing them. I'll be using the button on here to type them for me. The exercises, this is sort of what to expect. The exercises are about, in general, be like 5 to 7 minutes of me doing something, and then 5 to 7 minutes of you doing something, and then 10 or 12 minutes of me doing something, and 5 to 7 of you doing something. It goes back and forth. And a few stretches where I just keep talking for like 20 minutes and demonstrating things. If there are 20 exercises, a few of you, 10% of you will get to finish those 20 before we move on. So that means 90% of you, every time, you'll feel like, oh, he's rushing us. And that's on purpose, because if I wait till everyone's done, 90% of you will be bored. So instead, I'm going to move us along when only a few people have finished by then, and that's normal. And I've structured it so that the stuff near the end you don't need to know. There are even some optional exercise sections. And then I will go through the exercises afterwards, most of them, and explain what you might have learned there, just to talk about it, answer questions, etc. My background, I've been in IT for 30 years. About half that's been software development. About half my software development has been in dynamic languages, primarily Perl and Python. Most of my career has been on Unix, various versions of Unix, and then Linux when that finally came out and we all rejoiced. But the last 7 years I've been doing Windows in my day job, and so I'm running a Windows laptop. There's no Apple shiny thing on the back. Of course, back then there wasn't Unix inside those Apple shiny things. And I already asked you questions about what you do. Any questions before we get started? Okay, so I'm gonna, hang on. Oh, I think I have some announcements actually before I get started. Let me double check. Yeah, we'll have a break at 3, finish at 4:40. The tutorial survey, I will give you this link later, but there is one that we really want you to fill out after each tutorial to give us feedback both on the specific tutorial and just generally how can we make things work better. So this slide will come up again, that part of it. And that I don't want you to see yet. Oh no. No, I don't want you to see that. All right, so let's get started. So the first place I want to start is with names and namespaces, and we'll use dictionaries. You all know what a dictionary is in Python. In the first 20 minutes, you might think, if you think for the first 20 minutes, this is going kind of slow, maybe I'm in the wrong tutorial, hang on, it gets better. I'm going to go very slow and methodically the first 20 minutes approximately. And what I'm doing is I'm brainwashing you, because you are brainwashed by other languages, many of you, and you need to, if you want to understand stuff more easily in Python, I think it helps to have a certain way of thinking and even talking about what's going on in Python. So a list is a mapping from integers to objects. And when I say mapping, I mean like the old Venn diagram, you know, here's this thing and the arrows going over math from high school. So for example, and let me mention one other thing, that 0 over there, that's just telling you what line number on so we can keep up with the printout. And I can move around in odd ways if I need to. So you can ignore it. So month number to name is a list that maps from an integer starting at 0, 1, 2, 3 to a string. Very straightforward, and there are a couple examples. A dictionary is a mapping not from integers to, or specific range of integers to objects, but from objects to objects, hashable objects to objects. All right, and so we have month name to number, maps from the name of the month over to the number of the month. Okay, straightforward. So when you think about namespaces and names in Python, they're like dictionaries with some significant differences, but I'm going to make one here and run through a quick little example. So I've got a namespace now. It's an empty dictionary. I am going to add a key to the dictionary. I'm going slow on purpose. I'm going to add a key to the dictionary. The key is A, and an object to the dictionary, which is 7, the integer 7 object. All right? And what actually happens here is, well, I'll get to that later. And so now I've got, this is my current names, is my namespace, this dictionary I've got. I can access an element to get the value back out. I can look it up by key. I give my namespace the key, I get back the object. I can add another object to the namespace. Sorry, I can create another object and add another name to the namespace. And I can get that one out. And I look at the contents of the namespace. I can change one of the elements in the dictionary, which I'm calling my namespace, so that A, which used to refer to the object, the int 7, now refers to the int 8. And you can see its value there changed. I can pull the 8 out, put another one in, right? All very straightforward. And I can delete entries from my namespace, okay? And you see when I try to get something that's not there, I get a key error, okay? Straightforward. I just restarted the shell because I want to start over and show you that's exactly how you should be thinking about the namespace in Python, right? So if I look at my current namespace, it's an empty dictionary, and I only see the names. And you can ignore the dunder built-ins. We'll explore those later. If I say A equals 7, what I've done is Python sees this, it looks at the 7 and says, ah, that's integer literal. I'm going to go create an integer object that didn't exist before, probably. And then I'm going to go take the name A, which is a valid identifier in Python. So it's not quite like a dictionary where you can map any hashable to an object. You can only map valid identifiers to objects. And then I'm going to make that the key in my namespace A is going to refer to the object 7. Okay? Yes? What I mean is, A, you couldn't have, for example, 7 equals 7. So identifiers, names in a namespace, have to start with a letter and or an underscore, and can only contain letters, underscores, and digits. It has to be a mapping of allowed names to objects. I very carefully am not going to use that V word, variable, because that's where some people get tripped up. Okay. Oh, that's what I'm doing. Okay. Right? And so if I want to, here's just a little utility function that I added to see. You can look at the current names for it. So you could like when you do a dir, it just shows you the names. It doesn't show you the values. But here I can see them both as a dictionary. So it's kind of like when I had the dictionary A7. To get access to the namespace, if I want to look something up in that dictionary, which is the namespace, I just use A. I don't use quote A. I just say A, and it says, oh, that's not a literal that I know. That's a name. Therefore, I'm going to go look at the namespace. Just like before, you'll notice these are the same examples, A's and B's and the whole numbers. They're just paralleling, so you can see how this is working. Right? I can get access to something out, and you can see it's put new values in. I can change the mapping. A used to be a reference to the object 7. Now I've said, go create for me an object, which is the integer 8, and I want A to now refer to that. Okay? So I think I'm going to straightforward, just a few more examples to see what's going on. And I can delete things from the namespace with the del keyword. If I try to access something that's not in the namespace instead of a key error, I get a name error. All right? Okay. Start again. If you suppose I have a bunch of parallel variable names and I want to collect them together, well, I could do something like this. I can have Rx and Ry, right? Like there's the R name, and hung off the R name or associated with R, there's an X and a Y. Well, I can do it like this if I use a dictionary, and I can get at those values or get at the pair of values, and you can see it stores it that way. The equivalent kind of functionality in the Python namespace you can do is attributes, right? So here's a simple record class. I didn't inherit from objects, sorry. So it's actually an old style class, which most of you won't know what that is. Doesn't matter, all I want is the namespace. So I've got R equals record, and now I can say R.x equals 1, R.y equals 2, and I can access them. So that's the way you do, is sort of the parallel between what you might do in a dictionary and what you do in the namespace. And you can see that R is now in the namespace once I created it. Okay. So that's a brief brainwashing session on names, and I've tried very hard not to use variables, and it matters because if you think about variables in statically compiled languages, typically what happens is the compiler sets aside a chunk of memory, and then it puts stuff in there and takes stuff out, and when you refer to a name, a variable, it's accessing that memory. It actually compiles down to a reference to that memory, and what it does to that memory, when you do something like a plus, it says, well, let me check the type. Is that an int or a float? Because if it's an int, I have to do an integer add hardware instruction, and if it's a float, I have to do a floating point add hardware instruction. Python's not doing that with variables and boxes that you put values in. It's just creating objects up there in object land and names that refer to them. Okay, so let's look at objects and give you a little foundational review here as well. Everything in Python is an object. It has a single value, a single type, some number of attributes, a single ID. It usually has one or more names, might have 0, and those names might live in different namespaces. And it usually has one or more base classes. So I'm going to show you quickly some examples of int, float, string, tuple, and list. All right, so a single value. Here's the value 1. Right, and that object didn't exist, and because I just restarted the interpreter up here, I think I did. No, I didn't this time. But the point is, it's when Python sees that literal that it goes and creates the integer 1 if it doesn't exist yet, and then here's 1.0. So string, float, int, float, string, tuple, and list. It has a single type. So the type of 1 is of type int, float, str, tuple, and list. Has some number of attributes. So the object, which is the integer 1, which represents the integer 1, has a bunch of attributes on it, right? How much memory does the object 1 take? It's not a byte. It's not 32 bits. It's not 64 bits. It's more because it's got other stuff associated with it, okay? And this is, all of this stuff is associated with it through references, through pointers. We can look at, here's an attribute of this integer 1. Uh-oh. Right. It's not a floating point number. Python sees the 1 dot and says, that's a floating point number. I know how to parse that. Oh, I don't after all. So put parentheses around it, we can look at it. So we can see here's an example of one of the attributes of the integer object 1. It's a string which has new lines in it. Usually you would use the help command to print that, or your IDE would do it for you. It has a dunder class attribute. So when I say dunder, this is double underscore class double underscore, which in common parlance in Python circles is pronounced dunder. So when I say dunder class, I mean double underscore class double underscore. So the int 1 has a dunder class attribute with the value type int. The float 1 does too. That one you don't need the parentheses, interesting. The string does. Okay, here's an attribute of the string Mississippi. The name of the attribute is count, and it refers to a built-in method count of the string object. It's actually a bound method, but because it's a built-in, it doesn't say that. And I can get that function or that built-in method and call it with the parentheses and pass it an S and get a number back. There's an index built-in method for tuples, a pop method of lists, right? And a single ID. So every object in Python has a single ID. The ID of 1 is, ooh, that's interesting. That's a memory reference. In this implementation of Python, at least this particular version of this implementation of Python, that's not guaranteed to be a memory reference. It's just guaranteed to be unique. Somebody asked me when I was practicing this a couple days ago, is it guaranteed to be unique throughout the life of the running code? And I don't know if it actually is or not. Conceivably, there might be some reason why a Python implementation might want to, as part of its garbage collection, move stuff around. So if it did so, it would always make it consistent before and after the garbage collection, but I don't really know the answer to that. So a float, go create a string, a tuple, a list, and it has one or more base classes. There's an inspect built-in module that has a get method resolution order. I can say what's the method resolution order of the type of a string, which is the str type. And you can see it's string is a subclass of base string. So hello is an instance of string, is a subclass of base string, is a subclass of object. If we look at hello, the string hello, that object's dunder class, we can see it's of type string. And it actually is the same. Is says, are these actually the same object? So when I say type hello returns an object, hello.class returns an object, and str, if I just type it at the prompt, returns an object, and all three of those names refer to the same thing, because is true. That's what is. Is means they are the same thing. They have the same ID, not just that they're equal in value. The class attribute has a dunder bases attribute. Bases instead of base because it can be plural. And it's a tuple instead of just a single object because it can be plural. And we can see that it's got base string, and bases sub 0 gives us base string, not a tuple, but the object itself. And it's got a bases, which is object. So you can actually see how get MRR works. It just is following these attributes, these hidden attributes up the chain. This is the right way to do it, though. Just use get MRO if you really care. Okay, there's now a short exercise here for you to do a little bit of playing. And again, this, just a reminder, this section is pretty slow. It'll speed up a little bit. I just want to nail these foundations. So I will give you a few minutes to complete this. I will wander around, answer questions, and then I'll go through the same set of exercises. Exercises. That is page 4, starting at line 96, because I just finished 95. Yep. When you finish the exercises, go ahead and do the optional exercises too.
just created a variable j and looked at the length of my directory. It was 41. I deleted j, but the length of my directory, I mean, the number of variables is 3 on the objects.
Interesting. Do it again and look at the list and see why. So I is J says, are they the same object? So does is I a name that refers to an object which is the same as the object that J is referring to? Oh, for sure. So your question then is? Right. Yeah, we'll see that. Okay, I warned you I was going to move you along, so I'm going to go ahead and run through the first set of exercises, and then some of you will have already started the optional ones, but we'll keep going. You'll have a chance to do that. I equals 1, I, right, so this is all straightforward. J equals 1. So what did you learn here?
It's pointing to the same thing.
Right, so when you ask Python to go create an object if it's an immutable type, it's not going to go create 2 of them if it's the second one, right? It's going to go look, there's already a 1. I won't use a whole another chunk of memory to create the same integer, and the same is true for strings, okay? And that's because they're immutable.
Strings in Python are immutable?
Yep. And as are tuples, not their content. Well, no, okay. We'll skip that for now. And you can see that is and ID equals, that's the meaning of is. Dir of none is the same as the dir of object. That's kind of interesting. Well, why is that? So what is none? What's that? The object that is? Exactly. It's an object that has only one instance, right? So I don't know where none gets created, but presumably when Python starts up, it goes and creates an object and assigns it to none, and then everyone's happy as long as it's not different. It's not different than all the other objects. So it's probably just an object. I'm not sure if it has any differences beyond that. And instances of object as well, which is, so again, you can't tell too much from this. And one of the temptations is to go dig and figure out all these details. Well, I just want to dig enough to sort of get behind the scenes a little bit and understand and make things more clear when you're working above the surface of the stuff. But you can, if you ever need a sentinel value that's unique and different than any other possible object coming in, you can use just object. Like if you need none is a unique one, but you can just create a new one for yourself and name it something else. Okay, go ahead and take a couple more minutes and work on the optional ones if you haven't started those.
So the dir of none is the same as the dir of object, but the ID is different.
Right, so all that means is that the dir is what are the attributes of.
Right, true. So the attributes are the same, but okay.
The list of attributes is the same.
But they're not occupying the same space
And the values of the attributes.
can be different. Sure.
Yep.
Okay. All right.
I equals integer 1, and then I call ID parentheses I. Get back type error. Int object is not callable. I've done it 3 times,
Mm-hmm.
so I think that's the typo.
No, but just reminding you, you can't. Oh. Did you get that? Does that work for you? ID of I in object is not callable. Not doing ID of I.
That's bizarre.
That is bizarre. Restart and see if it still does it. That's right. Mhm. Oh, look.
But it's not the same as this one.
Right.
Is that expected?
It depends. And what it depends on. So is it expected the way, in terms of the IDs? So knowing what these IDs do, I'm going to move us along again. Knowing what these IDs, what ID does and what is means is kind of interesting, but you shouldn't care, right? We're looking, sort of lifting up, pulling back the curtain where Oz is pulling the levers to see how things are working back there, but really that's not our business. We should always work at a level of abstraction that's higher than that. That's why we use Python. So don't worry if, I'm teasing you saying, oh yeah, there's stuff that's going on back there, but exactly how it happens, that's up to the implementation and up to the time of day. I mean, sometimes you create a string and then you create another string, having thrown away the first one, and it comes out, it's at the same memory location as the first string you created, because it reused the memory. Other times it won't. You can't rely on it. So let's go through these optional ones quick here. Create a list M. So now I've assigned, I haven't assigned. I have made a new, so M, I gave a name M in my namespace to the list I created. And then I gave a name N in my namespace to whatever M referred to, i.e. now N and M refer to the same object, which is a list. And you can see there's M and there's N, and M and N. Like if I ask Python for M, it gives me back an object. And I ask Python for N, it gives me back the same object. They're the same object. That's what is means. Okay? So if I say assign M sub 1 equal to the string 6 instead of the int 6, and I look at M, I get 5, 6, 7. And if I look at N, I'm going to get 5, 6, 7. It's the same object. I changed the object. Assignment of, like when I did M sub 1, I'm changing the object that M refers to. N refers to the same object. This equals hello. No surprise. So sometimes this, in the past, at least with some versions of Python, would show up the same ID because it already got rid of the hello, reused it.
But it had to create a new one.
Yep,
The string removed.
that's right. So when you do a plus equal, so what it does is it goes and finds the hello string, it goes and creates the there string, it adds them together to make a hello there string, but the hello string and the there string are unchanged and possibly deleted from memory if they no longer have a reference to them, a name that refers to them. Some foreshadowing there. Oh, so I haven't done a from future import div. Oh, and I can't change it. So that's kind of reassuring that I can't set attributes such as what does the div method do of the built-in. Okay. Any questions before we move on? Yes? No, it just means that as long as there's a name that refers to it, it can't change. You can't be changed. It may get cleaned up. May not. We don't know. That's the implementation. The implementation of Python will decide that. That's not our. If we're worried about that, we're probably working at the wrong level of abstraction. Okay. Namespaces. I think I have a slide. I have a bunch of slides here. Okay, so we sort of saw how namespaces work a little bit. Now let's talk more formally about it. A namespace is a mapping from a valid identifier name to an object. It's like a dictionary. Assignment is a namespace operation, right? So CS 101, a while back, you're learning how to program, or wherever you learn to program. In a lot of other languages, what is an assignment? It's filling the box with a value. In Python, it's not filling the box with a value. Assignment is a namespace operation. It is changing a name in the namespace. It is not changing an object. Okay? A scope is a section of Python code where a specific namespace is directly accessible. So if I type A and I get back the contents, what A refers to, see I said contents, shame on me, then I know that I'm in a namespace. The scope, sorry, scope is here, that namespace is directly accessible because I can say A and it comes back 7. That means that namespace is directly accessible in that scope. For directly accessible, you just give its name, which I just told you. For an indirectly accessible namespace, you access values with dot notation, which we saw, right? So so R is a namespace. R refers to something which is a namespace, and R.X says look up X in the namespace that R refers to, right? Or sys is a name that refers to an object. That object is a namespace or functions like a namespace, and it has an attribute called version. So I'm looking up a name in that namespace, and it refers to an object that itself is a namespace, which has an attribute major or a name. Okay. The direct name search order is first innermost scope, local names in functions, for example. Second, namespaces of enclosing functions. Third, the middle scope contains the current module's global names. And the fourth is built-in names. So that's where it goes and looks. When you type A, it goes and looks in those 4 places. And what those 4 places are, it depends on your context. Okay? So let's look at a couple examples. Oh, but before we do, I skipped a slide. So all namespace changes happen in the local scope. And here are almost all of the namespace change. The ways you can change a namespace. You can do an assignment, which either will make a name that exists refer to a different object, or maybe the same one, or it will make a name start to exist in a namespace. Import, def for defining functions, class for defining classes, and del which removes the name from a namespace. Okay. So let's look at len. So you can see it went to that number 4 to find len there. So let's define a function, f1, which inside it has a function called len, which inside it has a local variable called len. And then inside function f1, we call that function, and we print out a few things because we want to see how it works. All right, so when we're in f1, len equals, and then we print, oh, it's this function right here. So by the time we get to here, the name len has been overridden, and it's a local function. And then inside this function len, we call len right there. And in there, we have a new name in the local namespace of the function len, which is inside the function f1, which is, we give it the string. And in there, we say, what is it? Well, it's the string len, right? So here's an example of overriding and using scopes and namespaces. All right. I'm looking at this because I thought I added a comment to that. I might have a version that is missing a few things. But the difference here is I took out the len equals string len. All right, so it's, again, this is just showing us that that's what those are at those locations. When f2 has exited, well, it lens back to the built-in function, right? It's only within those functions, the scope of those functions, that we saw the other values of that name. Okay? I can do that, though. And now len is 99. If I get rid of it, well, now it goes and looks in the built-in, right? So it's going between different scopes, whichever one it hits first. Okay? This is a bad idea. Don't do this, right? And this is a bad idea. Don't do this. But knowing that, like, when you do it, now you'll go, oh, I know what I'm doing, because I saw Stuart show me how bad that's a bad idea. All right? But you can, like, Python gives you enough, gives you more power than some people are used to yet. And it can do, yeah. Anyway, pass, it's just a keyword that says do nothing. It's like a no-op. So len equals 99 I can do, but pass equal 3 I cannot do. The reason is len's a built-in, pass is a keyword. So subtle difference there. Okay. Del is another keyword. This time it gives you, okay. So, function locals. Hang on just for 1 minute. Okay. Okay. Some of you will have seen this. Something like this, I mean. So x equals 1. Great. And now I've got a function test in which we print the value of x. So if I call test 1, it's going to say in test 1 x equals 1. No surprise. X is 1. Now I'm going to create a function, test 2, which in it, x equals 2. So if I look at x, it's 1. If I call test 2, what am I going to see? In test 2, x equals 2. Right. And when I get back out of test 2, x is 1. Right? So this name was shadowing or overriding that one in that local scope. All right. Well, let's do something pretty similar here. In test 3, what value does x have? And then we're going to say x equals 3. And when I call it, we check beforehand, x is 1. And afterwards, okay. So what's going on here is that when Python compiles the function, it sees an assignment of x. And it goes, you're assigning x, your assignment. It's saying, you're creating a name x that refers to the object 3, so x must be a local variable. So I'm going to say x is a local variable. Then it executes the code, and it tries to reference the local variable x before it has a value. And that's why you get unbound local error, local variable x referenced before assignment. Right? So this has to do with not namespaces and overriding all that exactly. It has to do with the fact that first it compiles the code and figures that stuff out, and then it actually executes it, interprets it. Okay? We can actually go look at that. Test 1 has no local variables. Test 3 does. So you can introspect Python and say, well, go look at that function code blob out there in memory. This is memory, by the way. I keep pointing up here because this is where memory is in Python for this tutorial. And you can see that x is a local variable. Okay? And this is not some deep secret. It tells us exactly what's going to happen. Well, almost. Right? So it's saying this is what happens when you have a local variable. It just starts ignoring the other one. The fact that if you try to read it before you write it, that's kind of weird. Eh? Yes?
If you did a dir on x in that situation, would it just still give you the same error message, or would it say...
dir only looks at the keys of my namespace. So if you did there, I don't know what it would do, because dir is kind of funky. Dir is not a very consistent function. It does what's very useful to you as a user of the REPL, the redevel print loop, but I'm not sure. Try it out, if you're curious. Don't get lost in the weeds, though. Remember, we're just peeking, and then we're going back up to the right level. Okay. I forgot to show you the list of keywords in case you were curious. The keywords? Oh, you can't. So don't worry about messing with these. It's the other ones like len that you can mess with, and you should just, in general, avoid them if you can. Okay. Oh, here we go. Okay, and now let's look at test 4, which doesn't do the weird thing with the local aerials. Here instead we use the global keyword, and as you all know, globals are bad, hopefully. So yeah, if you're using a global, try not to. Try to do it a different way, and you'll be happier, especially when it comes to trying to do things like testing. So x equals 1 beforehand. When I run test 4, it's going to say in test 1 before x equals 1 because I told it, always refer to the global one. Don't create a new local one. And afterwards, it made it 4. But when I get back to afterwards, what will it have? Still 4, right? Because I told it's a global. So This says, don't make a local. Anytime you see X anywhere, it refers to the one that's global, including on assignment, which is why it's such a nice feature when you really need it. And test 4 has no locals, you can see. Okay. The local namespace. So this section I'm going to fly through pretty quick. I'm not happy with it. And this is sort of the one section I'm still not very happy with. And I think I'm going to just change it into slides instead of a bunch of code. But it's we're basically, I'm going to show you some introspection. So I won't explain the code. You can go look at it later if you want. But I want you to see just what is there in the built-in namespace, in case you're curious, because I'm curious. So dir, I said, is kind of a weird function. It does funny things. It says things like, without an argument, it returns the names in the current scope. Otherwise, it returns an alphabet list of names comprising some of the attributes or attributes reachable from it. So it's kind of does some interesting stuff, but it's a very useful function. What's the current scope at the 3 prompt there, the chevron, the REPL? Anyone know? I think it's the global scope for the module, where there's no module in the sense that we haven't loaded a function, but later when we look at packages and imports, you can see how you can look at what the current module is. And it shows up in error messages, exceptions. So I do a dir, and I can see there's this built-ins. Well, what is the built-ins? It's a bunch of interesting things. However, I'm using Python running inside Python through code.interactive. So if you do dir, you're going to see a slightly different list. So I do this little hack to make it look like what you're going to see if you try this. And after that, I use my built-in instead of built-in, and it works. So first, let me get some, pull this stuff in, pull this stuff in. Okay, so the exceptions that are built in. Here are all the words, here are all the names that are built into Python that have the word warning or exception or error in them. So there's a whole bunch of what's in, like the built-ins is this much, and a whole bunch of it is exceptions, right? And then there's all the rest. Those are all the stuff that aren't exceptions, with a couple of exceptions a couple of exceptions that don't have one of those 3 words in it. And these are basically most of these are of 2 types. Those types being type, or a built-in method or function or method, right? So most of these built-ins refer to either a built-in type or a built-in function or method. And specifically, here are the ones that are types, and here are the ones that are functions or methods. So kind of interesting. And then there are a few odd ones that are neither of those. There's these ones, some of which you will only see, I think, in the REPL, I'm pretty sure. So that's just a quick overview of what's in the built-in space. So I'm not going to, built-in namespace. I'm not going to go into detail about it. What I will do is let you go play for a little bit. Try some more things out in the next section. refer to something else. It's a bad idea, but you can. All right, I'm going to hurry us along again because a few of you are getting close to finishing this section, and most of you aren't, and you shouldn't feel bad. This is normal. Remember, I give you this much to finish, and you only have time for some of it. But I'll go through it and show you a few things. So locals is a function that returns something that's kind of like the current namespace, like that my namespace function I defined earlier after I defined the my namespace dictionary. And you can treat it like a dictionary and actually add things to it like this. But you will run into problems, partly due to fast locals in functions, if you do that. So it's not a good idea, but be aware of it. I just had this thought of this analogy, right? I've got my 6-year-old son, and we're going for a walk, and we're like, oh yeah, we're going through kind of a dirty part of the park here by the creek, and don't pick that up, it might be sharp, and be careful about that, you might fall in, right? Part of what I'm doing today is I'm giving you the tour of these things that you probably don't want to go play around in, but be aware that they're there, because every once in a while you might need something sharp to go cut open a box, or I don't know. So you can actually modify the local namespace, and it's quite easy to do it this way and break things. I've got some examples. Inspect. Oh, so true is of type bool, which is a subclass of int, which is a subclass of object. Some interesting history of the Boolean type in Python, and the controversy it caused in a few circles when it was added. And some people thought it was a really bad idea because pedagogically it just makes it harder for people learning programming to understand if there's a separate type. Is_instance is a built-in function that lets you check for subclassing. So the only time I ever use locals is if I'm writing code that I'm going to run once and throw away, and I just have a bunch of local variables and I want to stick them in quick, and I can do it either that way, or I can just use ** locals and say, well, I just want the names. Let me just use the names directly in here and not make me repeat them over and over again 3 times, color, 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 right? I can just do it this way, and I get then inserted. So there's a use case that maybe I wouldn't frown at. Of course, if I ever reviewed the code, then I'd say, well, why are you writing that in code that's being reviewed? So not a good idea in general, but good to know. Occasionally it is useful. And then some of these things, when you get to a level and responsibility or where what you're supposed to be doing is writing libraries or certain kinds of other things, then some of the stuff behind the scenes can come in handy. But I find even knowing how it works and what it's doing as a user of the libraries is helpful sometimes. So namespace changes. Remember here the namespace changes, the things that change a namespace. And I added globals and locals in square brackets to be honest, that yeah, you actually can. Let's look at export. Sorry, let's look at import. That's what I meant to say. All right, so I've restarted my interpreter, and I'm going to import pprint. pprint is a standard module, a standard library module, so it goes and looks in the Python path and finds it and pulls it in. And what it does is, so what import does is it creates a new name in my namespace which refers to the pprint module having been compiled and pulled into memory. And I can see that, and it even tells me where it got it. I can look at the attributes of that namespace. Like a module is a great example of a namespace. So I've got this pprint name now that refers to that module, and it is a namespace. In that namespace, I've got all those, which I can just, and a bunch of them are dunder attributes, and then a few that are not. Now, some of you might realize that this dunder all means that this list may not be all of the things that were in the module. If there's a dunder all in a module, you can say, if someone does an import, I only want them to see some of my attributes. Oh, you know, I think that's wrong. I think that's when you do a from import star. I haven't used that very much, so I might have just said something incorrect slightly there. But here are the ones that are in there. And I can access attributes like pprint.p format to get at what is in there. Hang on a second while I make a note to correct. And I can see it's a function in that namespace. Sorry, I'm going backwards by mistake. And there's a pprint function, and if I do an attribute that's not in there, I get an attribute error. Module object has no attribute view. Interesting, it didn't give me a there's no such name in that namespace error, or there's, you know, it didn't give me any other, it just gave me a plain old attribute error, which is generic to lots of things. And that's part of the Python philosophy is, like, this is good enough. It's using just attribute access to get at this stuff. It's not doing some magic module access, I don't think. So that's why the error is not specific to the fact that preprint is a module. And of course, foo itself is not defined. And you get a name error in that case. So you may have seen that the import statement, you can put some extra things on it. You can say from the pprint module, the prettyprint module, I want to import pprint because pprint module has a pprint function, and I want to call it in my local namespace. When you pull it in, give it a name locally, which isn't pprint.pprint, but give it the name pprint underscore pprint underscore function. And now if I look, I can see there it is. And I can check, oh, yep, they're the same thing, right? So I've got pprint, the module got imported, and I went and imported something out of that module with a different name, but those two names refer to the same object. All right, now if we get rid of pprint and import it as pprint module instead of pprint, then I've got the pprint module and the pprint function. So again, these are just ways to sort of explore. Let's do lots of arrows and make things refer to each other and not. So suppose you want to do an import and you don't know until runtime what its name is. Well, you can do this instead. So the dunder import built-in function lets you use the functionality of the import statement, but calling it as a function. And now module name here, you could have gotten that from somewhere else or determine it dynamically, you know, at runtime depending on context or something like that. Right? So now if I look at string module, it is now the name in my local namespace that refers to the string module, the import of whatever string is, the string module in the built-in in the standard library, and it's got an attribute uppercase. I can look at it. Yep.
Just in the import preprint as preprint module, why was preprint not added to the div? Because in the first instance, when we were importing the preprint function, preprint was also added, right?
Yep. So when you say as, it says, so when you say import something, it will create the name something in the local namespace. When you say import something as something else, it uses that name instead. No, just the other one, just the second one. It says where to get it, but what to call it. It splits that out. By default, it gets it and calls it the same thing.
The preprint in the line 216 is actually the module.
Up here, it was the module.
That's
Yes. Okay, so I've imported the string module. So if I say, what is string, what's it going to show me?
Wait, where did you actually run it?
I import it right here. Import string.
Oh, that actually caused that to execute?
Yes, dunder import is a function that I have now imported module name, where module name is string. So I have imported the string module. So if I type string and hit enter, so what happened is it came into my local namespace as string module because I told it to, right? So import is a function that goes and looks for a module, imports it, and then that package, that module, it gives it back to you. And in this case, I said, yeah, please create a new name in my local namespace called string_module. That's what I want it to be named. Whereas if I had done an import string, this would not have failed, right? So trick question there, like many of my questions. Hopefully a learning opportunity. So, but if I do an import string, then it'll work, right? I think it would do it and then throw it away. I've never tried that. I'm pretty sure that's what it would do. So import string doesn't work. Why not? Because it's import string without the quotes, which actually now lets us look at this and say, this is kind of a funky statement. Import, what does import do? Well, Python sees the import and it goes and looks for whatever the import name refers to. And, well, sort of. And then it sees string and it says, oh, string, what does that resolve to? It doesn't even check. It turns that into a string, looks through the Python path to find a module that has the name of that string, and then turns around and takes that string and turns it into an identifier and sticks it in my local namespace. So that's actually what import is doing, right? So let's get rid of it. And so here's the opposite. Here's the other way to do it. So this is what import string actually does, is something like that. And there are imports really rich, complicated. There's tons of stuff in there that I've never gone poking around in. I think Brett's giving another talk this year on import, maybe. I can't remember for sure. But interesting stuff if you need to be doing that kind of stuff. We're just scratching the surface and seeing pieces of it. Oh, I think I have a slide now. All right, so now let's try importing some files that are in a hierarchy of files. I've got this file structure on my disk. I've got folder 1 with file1.py in it. I've got module 1 with 2 files in it. A dunder init.py, which is just completely empty. It just exists. And I've got a file1.py, which has in it a single assignment called attribute1. All right, so what happens when I do, and you may have to refer back to your sheet to remember what's hidden underneath there. If I do a dir, great. Okay, import folder 1. Doesn't work. Right? But I could do this probably, right? I mean, there's a file 1 in the folder 1 folder. There's a folder 1, and in there's a file 1. Still can't do it. Right? But I can say import module 1, and it works because there's a dunder init file. And there it is, module 1. I can look at the contents. Oh. So there's all these dunders, but there's no file 1. File 1 was it called? Whatever I called it. I did call it file 1 in both cases, but there's no file 1 in there. It's because the dunder init didn't pull it in for me. So when it does an import of when you say import and it finds a folder with a dunder init inside it, it will run that dunder init. And this one, it was empty. It didn't even open it to run it because it was 0 length run. Well, I don't know what it did, but the point is it didn't do anything. But I can do import module1.file1, just like I tried to do up here. And this time it'll work because there is a dunder init in there. It lets you do that. So I can look, and now module 1's in there, just like it was before. Oh no, it didn't even show module 1 in there. Oh yeah, it was. Sorry. So module 1's in there just like before. And I can look at module 1's attributes, and I can see that file 1 is in there. And I can look at module 1 file 1, and it's got the attribute 1. I can also do from module 1 import file 1, and then that pulls file 1 in at the top level. Okay, so lots of ways you can do your names when you're doing imports. Yep.
When you do from module 1 import file 1, then it doesn't take that attribute 1 name into the top level namespace, just into the module namespace?
Yep.
Oh.
I'm pretty sure that's right, if I understood the question correctly. You go double check it though. So here we have it because we, oh no, we don't. So imports code style, PEP8 says a lot of stuff like that. I told you that about int.py. And now you get to do a few things with the import statement. So one thing I forgot to mention earlier is when you're doing the exercise I asked you to do, only do them if it makes sense for you. Right? If you see one, you're like, I know what that one does. Skip it. Go to one that's more advanced. The whole section's like, yeah, I get this part already. Do whatever you want to help you learn during that time. All right, I'm going to hurry us up again. Most of you will not have finished. So anything interesting in here? So you can see that when you import a module, it has a bunch of Dunder attributes that are kind of interesting. The from pprint import star is convenient, not recommended for code that's going to be around for a long time. PEP8 says don't do it usually. But it pulls all of them right into the top level. So reload CSV, what does reload do? Reload's kind of an odd, I don't know what the history of reload is exactly. I mean, well, I can infer that it's there so that you can reload a changed module. So if I tried import space CSV, it would do the right thing. Reload as a function, and I pass it CSV, what's it going to do? CSV isn't a name yet, right? It doesn't know what CSV, so it tells me so. Well, so I give it the string. You have to give it a module. Okay, let's import CSV, and then let's reload. Now we're giving it a module, right? No, I gave it a string. It's still going to complain, right? Fine, we give it the module, and then it reloads it. And reload has some interesting semantics in terms of, like it may not always do what you think it will do. Like if you import CSV and then add some stuff to CSV at runtime, like in your code, and then you change CSV and you reload it, those things won't go away. There's one example of some of the oddities that are in there. Import sys. So sys.path, this is where it goes and looks for, on my machine, where it's looking for packages. That's what I mentioned the Python path earlier. Python path is an environment variable that influences this value. Okay, let's look at functions a little bit. Any questions before we go on? tried to run sys.file? Huh, interesting. It may be that sys is built into the library, the language itself, as opposed to a module. I didn't realize that. That's my guess. Or it may be how it got it, because I know, like, you can get, when you do imports, it can get stuff from lots of places. It can get stuff from like a .pyd file if it's an extension, or it can get stuff from a zip file if it contains a .py file. And so sys maybe, I'm not sure where it actually gets that. But it makes sense that maybe sys comes from, it's built in, just not always visible. That's a guess. I'm glad you tried something and it failed. So let's just do a quick review for some and maybe new stuff here for others in terms of arguments. So in Python, of course, you can pass regular arguments, you can pass keyword arguments, and you can collect wildcard arguments, let's call them, like the extra ones. So I'm just defining a function that prints out what it got. So if I look, but before I start using it, I'm going to notice that what happens when you define a function. Remember, because a function is a namespace. Defining a function, def, is a namespace operation. Right? Well, what's the namespace operation? It's not only a namespace operation. What did this actually do? It did two things. It evaluated all this code, compiled it, didn't actually execute it, and created a function object, code object. And it changed the local namespace to have the name f. The name f didn't exist before, now it exists. Right? And that object, that code object, that function object out there, has an attribute called name, and it actually gave that name, that code object gets that name as well. So the name f now goes two places, into the namespace and into the code object that got created. Right? So you can see f got inserted. So this is namespace. That's sort of the thread that ties a lot of this together. You can override it if you want. You can change it to something else. And you might think, why would you do that? Wouldn't that be a bad idea? Actually, it's really a good idea sometimes when you're creating a function on the fly, and what its name should be depends on what you were told to do on the fly. That would be an example, and I'll show you one later, where it is a good idea to change a function name in those relatively rare cases. But of course, I've only changed the attribute over there in that code space, right? I haven't changed the local namespace just by doing an assignment. So I still got f as my local name. Right? But when I say, what does f point to? Well, it returns the object, and Python's got this object that its name is g, because I changed its name to g. Okay? There's also something called funcdict in a function. And more importantly, maybe I should have done this backwards, f.foo did not exist. There was no foo attribute. I just created it. So functions are a namespace, and you can use them as such. And that's used occasionally for some features of some packages. And then you can actually get at all of those ones by looking at the funcdict. So be aware of that. Funcdefaults tells us something about the default arguments. So let's call this thing a few ways. f12, and you may have to go look at how we define it to remember, but arg1, well, it shows. I put it all right back in here. This is what the arguments were. So it left these, and these are empty. arg1, arg2, I can use the names if I want. No change to the values of the arguments. I can switch arg1 and arg2, and I'll actually get the 2 followed by the 1. So I can reorder stuff with the keywords. And I can call them and add this one, overrode that one, even though I didn't use the actual keyword arg1 as the parameter name. And I can skip them if I want. So it left this as default and changed that one. So this is, just if you've used Python very much at all, you will have seen this kind of stuff. I'm just sort of exploring all the possibilities here, including ones that will fail, right? Like you have to pass it you have to pass it 2 arguments before you start passing it a keyword argument. Well, I didn't say that quite precisely, but I think you understand what I mean. I can pass it all 6. I can give it some new ones, and they show up over here in the KW-args dictionary. Sorry, I think I said that wrong.
So if you give it general,
Oh, here's it. I put in the args 5 and 6. I stuck those in there.
and those just turn into an extra tuple.
Yep. So those extras are going to show up over here, whereas these extras showed up in the KW-args. Okay? Okay, so short exercise for you to go play with functions a little bit.
Oh, never mind. Sorry.
So in this case, we've got, sorry, looking here. So you've got positional arguments and then keyword arguments, and then you've got star args and star char quarks. Is that just the convention? Like, because then you can have arguments, keyword argument, or positional arguments after your keyword arguments, or does that instead come?
Yeah, the location of these does matter.
Okay.
The only thing the convention, I think, is just the names.
Yeah.
I don't know all.
Because I would almost expect it to be arg1, arg2, star args, arg1, arg2.
Yep.
That's not.
Right, because if you do that, then you limit what it can accept as arbitrary extra arguments.
Okay. Smart enough to figure it out. Okay.
Yep. All right, let's keep moving. I know you're not all done. So, a couple simple examples just to repeat some of what I showed you. And then, of course, not only can you collect arguments, you can expand them, take a tuple and say, please unpack this and pass them as arguments. One of the great things about Python, the tuple unpacking. Right? And then the same with dictionaries. You can pass a dictionary and say, well, turn this into the keyword arguments on the way in. This one you may or may not have seen. What's going on there? And the answer is, this arg equals the list with a single element 0 is evaluated when the function is compiled, when it's first evaluated, not every time it's executed, right? And that's a gotcha that you need to watch out for, which occasionally is actually used to someone's advantage, but usually is confusing, and there are other ways to do it. So every time I call it, it's actually, this arg starts out with the list 0, and then I change arg with the list with the element 0, and then I change the 0th element to be 1, and then the next time it gets called, that same thing. It's always referring to the same list. It only got created once. So that's confusing if you haven't seen it. All right. List, strings, and in-place add. First let's just go back. S1 equals S2 equals hello. That's just a shortcut for saying both S1 and S2 are names that refer to the object hello. Now let me slow down here and say it very precisely. I'm going to evaluate S1, which is the string hello. I'm going to create a new literal, and it will go out there and get me the hello string. I'm going to go create a new there string. I'm going to add them together to create a new hello there string, and I'm going to change the name in the local namespace S1 to refer to that new string I just created, right? So now S1 and S2 should be, S1 is still hello. Sorry, no, S1 is now hello there, and S2 should still refer to hello. Good. All right. Now let's do it with the plus equal. Plus equal is, it's like S equals S plus there, right? So S1, S2, hello there, no change. All right, let's do the same thing with the list. ME1 equals M2 equals 1, 2, 3. Let's add 4. Let's add the two lists, 1, 2, 3, and 4. Those two lists together, we get the list M1 should now refer to a list 1, 2, 3, 4, whereas M2 still refers to the old list 1, 2, 3. Good. Start over again. Do M plus equal instead, and we should get 1, 2, 3, 4, 1, 2, 3. But we don't. Why don't we? So it's an interesting thing, and it has to do with a couple things. Primarily, it has to do with what is the meaning of in-place add, and a side effect, historically, of the fact that lists are mutable and strings are not mutable. Strings are immutable. And let me show you exactly why. So f plus equals 1 is not the same as f equals f plus 1, or foo equals foo plus 1. And let me show you what it actually, where this goes. Code op and dis, I'm going to compile some code and then disassemble it and see what it looks like. So those two commands, those two statements, in place add, right? So this did not compile into an assignment of a, s equal s plus 1. It compiled into, m in this case. It didn't compile into m equals m plus 1. It compiled into m plus equals 1. So plus equals is a different operator than just syntactic sugar. And if we do the same thing for the s, the string, going further back, we get the same thing, in place add. So in both cases, it's in place add is what this thing actually compiles to at the byte code level in the Python, that the Python interpreter interprets, the virtual machine. Okay, so list 1, 2, 3, it's as though I'm calling dunder I add with the list 4 as an argument. I'm calling the method dunder I add, which exists on the list instance 1, 2, 3, passing it a single argument, which is the list 4. And it returns a value, which is kind of interesting. And now we see that m is 1, 2, 3, 4. If we say s equals hello and we do s dot dunder I add, it doesn't even have one. So the string type doesn't have a dunder I add method. So let's go read what the documentation says, if I can get there. Calls IAdd only if it exists. Otherwise, it is replaced with s equals s plus 1. So that's what's going on, right? So if the object, and here's exactly what it says down here, these methods should attempt to do the operation, well, it says more, but the point is, what does plus equal mean in Python? It means go call the IAdd method. If it doesn't exist, then change it to plus or equals whatever plus whatever, and do that instead, right? Now, why does the list m have a dunder IAdd and the string doesn't? And that's because these methods attempt to do the operation in place, they should attempt to do the operation in place, modifying self, and return the result. Remember, a list returned the result, which could be but does not have to be self. And then it goes on. I think I might have cut off. But so now you can see why string doesn't have dunder IAdd and list does, is because what would a string attempting to do the operation in place modifying self mean for an immutable type, right? So that's why these are so different. Which, and again, is this a, I think this is sort of on the borderline between something that's interesting and curious and something that's a wart. I think it's not quite a wart, but it's in the, like why are strings immutable? Because they're faster. That's one of the main reasons. So it's a compromise. Okay, so now what about pass by value or pass by reference? How does Python pass parameters to functions? Oh, I heard someone say depends. Don't tell me who you were. It doesn't depend. You know how it passes them. You do know now, I think. Let's find out. All right, so test S1 before and after. S1 equals hello. S1, sure enough. So S1 is a name that refers to the object hello. So when I call test1 with S1, Python reads the S1 and does what? Goes and looks it up in my namespace. What it gets back is an object. And what does it pass to test1? The object. In this namespace, S is a local name that is going to refer to, it's going to be a name for, it's going to point to the object that got passed. So it points to the same object that S1 was pointing to, right? So before it's going to say hello, and then it's going to S plus equal there. So at this point, S is going to refer to a new object, which is hello there. And when it prints that object, it's going to show hello there. Before it's hello, after it's hello there. And did the object that was passed in change? No, it's immutable. It can't. How about if we do it this way? Instead of calling test S1, we call test hello. That might make it more clear that it's not going to change the string hello, right? It can't. It's an immutable object. If we do this with the same code with M instead of S, and the plus equal 4, and I'm going to set M to be a list beforehand, and I call test2 of M. Well, you know what's going to happen, but do you know what M1 is going to be? Think about it. And why is it changed? Because the object that was passed in, it's not quite only because it was mutable. At the root cause is, yeah, because it's mutable, then plus equal, right? You go down the chain that we've learned here, and you see that, yeah, what happens is the object 1, 2, 3, the list 1, 2, 3 is passed in, that name refers to it, and then that object is asked to modify itself in place with the in place underscore add bytecode in the Python interpreter virtual machine, and it does so. So the object just changed itself like it was supposed to, right? So the answer really, I would say, and you can go debate the semantic or the terminology, but it's not really passed by. It's just cutting in and out occasionally. It's not really passed by reference or passed by value. It's really passed by object reference is the way some people call it. Well, it doesn't matter what we call it. Hopefully you understand it better now than you did. Okay. Change gears here. We got about 15 minutes till the break. Decorators. You've heard of decorators. Some of you, anyone who here admits to still being confused by decorators? Honesty is great. Fail fast. I will admit that in my academic career, it was always the theory courses that I was the worst at. And in my working career, it's been the same. And decorators, I kind of had to scratch my head for a long time. And it was when I was preparing this that I came up with an example, not trying to demonstrate decorators. But for me, it's like, oh, now I get it, which is kind of sick. And you'll see why. You'll see why when I show you what I'm going to do. So anyway, a decorator. So a function square, which you give it what? What am I passing in? An object, thank you. I'm passing in an object, right? And what's it going to do to that object? Oh, somebody said multiply. No, it's not going to multiply. It's going to apply the star operator to it, right? Because it might be multiply if they're, so that's, again, just thinking about what exactly is going on here. Because the point is, you could call this with something other than an int, and it might do the right thing. Well, in that case, no, it won't, because star with itself, I think only ints and floats can do that, and complex, in terms of the built-ins. So anyway, you call square 2, and we're going to get back 4. Square 3, we get back 9. All right. So this is a function that defines a new function and returns that new function. The new function that it defines on the fly, what it does is it calls the function that was passed into the identity function, and whatever that function that was passed in returns, it's going to return that. That's what the function, the new function that's going to be returned from this function does. All right? Right? And at this point, some of your brains are going, oh, well, think about it, right? This is what's going on. So I'm going to get back a new function. So str1 What will this do? So let's walk through it. Don't answer out loud. So identity, I'm going to call it, pass it string, the str, which is a built-in name, which happens to be a type, sort of a class, and you can call it as a function. So it's going to take that, and it's going to create a new function, f, which takes something. So I've created a new function, f, which takes something and returns str of it. And that, so the new function is going to come back. So this identity str is going to take the string function and call it on the 1. Right? So let's just give it a name. Might make it a little easier to think about. Right? So g is the name of the new function. The new function, I'm going to give the name here, g. And I'm going to say, well, make that function be what? Well, it's just something that, what does it do? It calls str. I think yes, right. So it's going to, g is going to be, is it going to be the same as str? No, because it's actually a function that calls str. So it's sort of, we've wrapped the function with something else that calls what we passed it, which is a function. Okay. So, make your brain hurt a little bit more maybe. Maybe not. So let's create a new function here, which is call string on. This is going to do something different than the identity, because it's actually going to not just call the function and return whatever it had, it's going to call the function and then call str on it and return that. So given any function, oh, by the way, what value does n have when this call string on is executing? Let's go find out. Let's print it. Defining new f, print n. What's it going to say? Exactly. Global name n is not defined, right? And that, for some of you, that might help you understand what's going on here. Is n is just we're just defining a function, and you don't know when you define a function, you don't know what it's being called with because no one's called it yet, right? So this function new f hasn't been called yet when we call string on. Okay, so let me change that code to no longer print n because that's nonsensical. And just so this is the same function as the first version with a bunch of print statements added. Trust me. So square is a function. Remember what it does? Square done underscore str is going to be, I'm going to take the square function, pass it off to this thing, and its return value I'm going to assign to the new name square str. Aha. So defining new f, it then defined it. It then call str on the function square, which is f that got passed in. But you notice, of course, this never got executed because we haven't called that new function yet. We just stored it in square str. And we can look at it, and it says function new underscore f. Remember earlier when I said sometimes it would be appropriate to change the name of a function? This would be a good candidate. What would be a better name than new underscore f? Yeah, and we can get the name square from the f that got passed in, so we could do something like that. There's an example of where you do want to muck with the name, but I didn't. Okay, so now if I call square underscore str, which is this function here, sort of, this function here, except that f right there has been bound to square, and called new function. The new function got called with 2. That new function was this function that has an str stuck into it, and it returned 4. So square returns 4. Square under str returns the string 4 because it called str on the result before it gave it back to you. So it took a function and wrapped it with something extra, some extra functionality. Get it? Brain still might hurt, that's okay. So square str2, square str3. So call str is a function that takes a function and returns a new function. In Python, the easy way to do that, this is, you can completely legitimate to do this way, but there is a decorator syntax. @ the name of the function to call, followed by a regular function definition. right? So you can see what happened. You might want to review this later if you still don't get it, which is, I expect that many of you still won't, because it takes a while to get used to thinking this way, if you're like me at least. So you can see that it created a new function, but the extra piece here is what name did it get? Up here I said square str equals call str on square. Down here I didn't tell it where to put the name. What name is it going to use? Cube, right? So a decorator calls this function on, defines a function, hands it off to call str on, and whatever that returns is that object that gets created, that function object, gets a new name in the local namespace, which is the name of the function that I passed in there. So cube now is a name in my local namespace, and it does what you think it would, because it's got that call str in front of it. It says take whatever returns whatever a value, call str on it beforehand. So that's what the call str on decorator does. Just so you know, this is kind of here's a more common example. I think I was going to show you that later, actually. But I'm not going to go through this, but memoize is a common example. What would you use a decorator for? Well, here's what you could use a decorator for, and I'll let you think about that later. Okay, so now that your brain's hurt a little bit, I'd like you to go do the exercises on page 16 and make them hurt a little bit more. But it's really cool, I think. Some of you will have some aha moments, and some of you won't. Make sure you think about what it's going to do before you hit the enter. See if you can figure it out. Okay, let's walk through this together. So why am I making you think this way? I think it helps. It's like, why do little kids play with blocks and tip them over and see how they don't stand up and see how they do stand up? Like, it's partly just playing with the concepts and making you think about them in a way that's not the expected way, which makes you really think about what is it actually doing and what is it doing with namespaces and names and functions, etc. So I've restarted the interpreter and there is no X in my current namespace. Then I'm going to turn around and define a call function, which just returns whatever you pass it. It calls whatever you pass it and returns what that thing returned, right? Now, int is a built-in type, which you can also call as a function. So if I call int, I happen to get 0. So if I call, this failed, of course, because it's a typo, right? Why is that? Again, get you on your toes here. It's because you can't use 0 as a function. So what I really meant to do is this, right? Call int. So pass int and then call int, as opposed to pass 0 and call 0. So let's call int and I get 0. Okay. Now, what does this do? So it's going to define, remember what it did with call str on, or cube, remember what it did with cube, right? So this function is, so def x return 3 is going to be a function that's going to get defined. It's going to be a code block, a function object out there. That function is going to get passed to the call function. The call function is going to take that function, call it, and return its value, which is not what decorators are supposed to do, but it's what we told it to do, right? So it's going to return the call function when passed. This function is going to call x and get back a 3, and it's going to return 3. And what the decorator then does, the decorator syntax, is then it's going to define x to be whatever call returned. Right? So there's the x, just got inserted into our namespace. It wasn't there before. And it's got the value 3. Right? So clearly not the way you're supposed to use decorators. But it helps you think exactly what is going on and why do decorators do what they do. So all a decorator is doing is taking whatever this function gets defined as, passing it off to this function, and the result of that is going to get the name x in the local namespace. Yes? That's right. The function x that we defined here no longer has anything. Yes, that's right. It no longer exists. Yep, which is different than the other cases, right? In the other cases, it was still somewhere because it was referenced in here. Because in the normal case for decorators, we have some functionality. We want to add something to it. So we save that functionality until we're actually called. Then we use it and do something extra. Whereas in this case, we threw it away, and the garbage collector probably did too. Good point. So the type x is int, just to prove it to you, right? So let's do this. This is another way of doing it. We could just do a def x, which returns 1 in this case, and say there's the function. And if we do x equals call x, x is now 1. Like that's if you're doing it the other way. Like started with before I showed you the decorator syntax. Now I showed you the misuse of the decorator syntax, and I'm showing you the way we could have done it without it. There it's probably more clear, but the in-between one helps you think about what decorators are doing. I think that's the last. Yes. Okay. We have a 20-minute break from 3 to 3:20. I'll be around if you have questions. Come back if you're ready for more. Oh yeah, so I can. Test 1, 2. Test. I don't think so either. I just turned it on. Maybe he turned it down. Battery says red. I wonder what that means. No. No amplification. Test 1, 2. Test. Test 1, 2. Test. Test 1, 2. Test. Test 1, 2. Battery red. Does that mean replace battery? Test. Cool. Since it's going red anyway. Test. 1, 2. Test 1, 2. Okay. All right, it's going to get faster and weirder now. Let's see, where are we? The class statement. What is the class statement? So, everything in Python's an object, has those things as we saw earlier. Many objects are instances of classes, and the type of an object is its class. Metaclasses, by the way, classes themselves are instances of metaclasses. That's what a metaclass is. Are classes and metaclasses objects?
Yes.
Everything in Python's an object. So the class statement, what it does is it starts a block of code which creates a new namespace. Within that code block, any assignments and function definitions happen in that new namespace that got created. It then takes that block of code, puts a new name into the local namespace, and then the class object that gets created is what that new name in the local namespace refers to. When you instantiate a class, you call them like they're a function, kind of, pass some parameters if you want. The dunder init method of the class is called automatically and actually gets as its first parameter the object that already got created by Python by calling dunder new, which you may or may never have heard of. I've been using Python since about 2005. I've only ever used new once. It's not a common method that you need to do anything with, but every once in a while you might. Method access, accessing an attribute method name on a class instance returns a method object if method name references a method, which is either in the class name or its superclass. What does that mean? We're going to find out. A method object binds the class instance as the first parameter to the method. Okay, let's see if we can figure out what these mean by descending into Python. All right, here's a simple little class called number, subclass of object. It so this class statement creates the whole block here is a new namespace. Namespace operations such as assignment and def that you see here happen in this namespace. and then the name number, which was not in the local namespace, just got inserted into the local namespace. So now there's a name cut out. When I turn, sometimes it cuts out. So now there is a name number that got put into the local namespace, which references the class object that got created. Okay, and this has a dunder init that just takes whatever you pass it as its second argument, first argument when it gets called in class, and stores it in a local attribute. It's got an add method that just takes whatever the number is and adds whatever you passed in. It's got a little version thing, and it's got that doc string. All right, so number is now in the namespace. You can access attributes of it because it's its own namespace. It's got this dunder init method, which is an unbound method, number.dunder init. It's got add as a method. It's got a bunch of other stuff besides add and dunder init and dunder doc that I actually also gave it with my doc string. And you can do help on it, and it gives you a bunch of information about it, which is a lot more than just what we put in the doc string. Okay, let's create an instance. So we name the class, open paren, close paren, pass a parameter. So, ta-da! So what happened was, so 2, I'm going to walk through this really slowly. 2, Python saw that literal, went and created an integer object. It saw the call to the class, and it went and created a new number object. It then passed those two things off to the number.dunder init method, and then the resulting, when it was done with that dunder init method, then the object, which may have had some stuff done to it, like the amount.self.amount was set, that thing, num2 here, just refers to that. Simple enough. So I can now look at num.amount. It's going to equal 2. Num2 is this number object. It's got a dunder init, which is in this case a bound method. Remember, capital N number was number.dunder init was an unbound method, whereas num2, the instance .init, a dunder init, is a bound method. It's got an add, also a bound method, and it's got all these things. It's got the add, it's got the amount. It does what the class does. Remember what dir, how it says some of the attributes up the hierarchy, right? So most of these don't live, most of these attributes don't actually live on the instance itself. Most of these it's getting from the class, including all the behavior, as opposed to the instance variable or field is associated with the instance itself. There's this, and that's actually how it's associated. There's this dunder dict that you can go look at what they are. The class itself has a dunder dict, but it's some other weird dict proxy thing we're not going to go look at. I just wanted to show you it's not the same. Okay, so num2.add is a bound method. And I can do that, and I get 5. Number.add is an unbound method. Warning, don't do this. Can I do that? Why not? Right. So there's no self. So what's the signature of the add method in the number class? How many arguments does it take? 2. It takes self and amount. Oh, it never even gets that far. It says unbound method add must be called with a number instance. So it does some checks before it even gets to the fact that the number of arguments is incorrect, right? So let's, and this is clearly going to fail too because it's the right number of arguments, but it's still not calling it with a number instance. So same error there. Can I do that? Why not? 2 arguments, needs 2 arguments. Can I do that? Yeah, and it works, right? So that's the long way around. Instead of just saying num2.add, I could say, well, number.add num2. And occasionally you might want to do that if you are trying to figure out where up in the class hierarchy to reach to actually do a specific functionality, a method call. But of course, this is what we would usually do, num2.add, because it's already bound together. Oh, now it's not only unusual, it's going to get weird. Set double amount is a new function I just created. it takes two arguments, which internally are going to be called num and amount, and it's going to take the first one and look for an attribute on that first argument, which is the amount attribute, and then it's going to take the second argument, multiply it by 2, and assign it to that, the attribute of the first argument. See how it's cutting out when I turn my head sometimes? Okay, number dot dunder init is that, not anymore. That's the right answer. You should not do this. This should make you uncomfortable. But it'll be interesting. We'll learn some stuff and I think help cement your understanding of what's really going on. So I've just made number dot dunder init. I just stuck that function in there. Right? Well, is this any different than what the class statement already did? The class statement, it just, right? Remember what we said, what does the class statement do? It has a block. In that block, it's a new namespace. Assignments happen in that namespace. All right, well, I just did an assignment of a new name in that namespace of a function. Unbound method. And it's, I can look at help on it. All right, so now let's do num4 equals number 2. And the reason I'm calling it num4 is because I've just changed the meaning of its dunder init to double what comes in. So I'm hoping that num4 actually is 4. Okay, so now it's calling my new dunder init method. And if I do an add, it works. Num2 dunder init is a bound method. All right, let's do it again. Multiply by num and value, return num amount times value. And again, the reason I'm careful, I'm not using the word self there, but it works. It's the right signature because I know, well, where I'm going to put it in that class, it's going to have the right thing. So let's try to stick this one in, but we're going to put it on the instance. num4.mul equals multiply by. So num4.mul, what was num4.amount? Oh, sorry, num4.add. A bound method. Well, what's num4.mul? It's just a function. What's different? Num4.mul5. Well, it's a function. It takes 2 arguments. You only gave me 1. Okay, I'll give it 2. There. Now it works. Okay. Let's say num10 equals number 5. Num10.mul. So what's this one going to be? Right? I did num4.mul equals multiply 5. Num10, yeah, I did it to the instance, not the class that it was instantiated from. And if I look at num4, it's got, well, num4's got an add, an amount, and a mul. And number's got only an add. It doesn't have amount, and it doesn't have mul. Amount doesn't have because that's the dunder init that creates that instance variable. The mul it doesn't have because it was never added to the class. Sorry, here. The mul is here in the instance, but not up here in the class. It's missing down here. Okay, so we'll fix that. Number.mul equals multiply by. Now, what will this show you? What's going on? Oh, now I'm really messed up, eh? I have totally mucked things around. What did I do wrong? Dir num4 has a mul. Num4.mul. Oh, so when I do a dir, it shows me the attributes on the instance and attributes on the class of which it's an instance, and attributes on the superclass, and it goes on up. So when I look at num4 and I see a mul, I'm thinking, oh, good, it's got the method because it's up there in the class, but I don't. I have instead an attribute mul on the instance, which is a function. But it's the same. What's going on? Well, at least let's fix it, okay? Let's get rid of num4's mul function. And now num4.mul should give me no such attribute, right? No, now it finds it in the superclass. Sorry, not the superclass, in the class. Now it finds it in the class. Now it's looking in the right place. And you notice that it was the same function, but I get a different thing, right? Num4.mul, I set to multiply by, and number.mul I set to multiply by. But here, when it gets it out, it says function multiply by. Here it says bound method number.multiply by. So that's the magic in Python of method access on an instance. When you say num4.mul, Python goes and looks in the dictionary for num4, and if it finds something, it gives it to you. If it has to go, if it doesn't, it goes to the class or superclass op, and if it finds something there, it says, oh, I found it up here. I'm going to return a wrapper around that thing, which is a bound method, as opposed to the function itself. I'm going to return a bound method, and the bound method does some extra stuff. It wraps it with some information that's useful. Whereas if I look at number.mul, it's an unbound method. So here it's saying it's unbound method, bound method. It doesn't say function here either. I'm not sure. I don't know what's actually different there. I haven't explored that ever, but it may do some other wrapping as well. Okay, so now num4.mul is going to work. So what does the wrapper look like? Well, num4 has this mul bound method, which itself has a bunch of stuff, including IAMSelf, IAMClass, IAMFunc, and a dunder self, and a dunder class, and a dunder func. And some of these are old style and new style names. If I look at the class, so remember what num4.mul is? It's a bound method. Num4.mul is a bound method. So it goes up to the class and sees a function hung off of it, and because it got it from the class when I referenced it through the instance, it gave me a bound method. There it's really cutting out. Let's try just turn that a little bit, see if it's down there. So it's a bound method, and that bound method has an IAMClass attribute, which is the class it's a part of. It has a self attribute, which is, the number object itself. Oh, which one? This is num4. Oh yeah, it is the same. Yeah, see, same. So this is actually the hex ID memory location, I assume. I'm 99% sure of that. Right? And it's the same thing, right? So the bound method already has a reference back to the thing that made the binding. It's kind of weird. And IAMSelf and self happen to be the same thing. It also has a reference to the function, the real code. It's not gonna, it doesn't copy it. It just says, well, I've got that code plus whatever else I'm wrapping it with. And it's the same as the multiply by, because that's how I set it up. And IAMFunc and func happen to be the same. I can go look at help on that. It gives me the help for the function. Okay, so when I say num4 mul5, meaning please call the method mul with the parameter 5 on the instance num4 of the number class, this is what it's doing. Roughly. It may do other things behind the scenes that are a little bit faster than this. But the point is, this is what the wrapping does. This is why a bound method has the information it needs, right? Is because that bound method that got returned when we went up the chain, it came back down and gave us something that was wrapped. It knows how to get the object itself, and then it passes the 5 across, and I get the number. All right. What's next? Exercises the class statement. All right. So there are cases where having a bound method is kind of handy, and the first part of the exercise showed you that. This is one I added a few days ago, so happy to hear if that works for you or not. Take 4 or 5 minutes to wander through this exercise. It's every time I turn my head to the right, which makes me wonder if it's a loose connection somewhere.
Maybe.
Yeah, just to be aware. I don't think it's bad enough to change out right now, but test. Yeah. Well, if it's by turning my head, then it's probably not this. It's probably some up here. It's probably one of these wires. Well, that's my guess. Okay, I'm going to walk you through the first part of the exercise. If you want to keep working on prefixer afterwards, I'll give you a couple more minutes for that. Let's just see what that first part's doing. So import string. What's going on here? So dict dot under doc, I just needed a long string, so I got one. And that string has a count method. What kind of method would that count method be? Bound or unbound? Bound, because it's accessing on the doc refers to a string. That string is an instance of the string class. Now it has a slightly different name when you look at it. It doesn't say bound method because it's a built-in class as opposed to a Python class for efficiency reasons. But it's a bound method. And if you remember or look up how sorted works, sorted, we're saying please sort that sequence. And sort it, the way you can tell how to sort it is not by the, don't sort A less than B and B less than C. Instead, sort based on the result of this function call on each of those characters. So it's going to call this function, bound method, with what argument? It's going to call it with one argument. What argument it's going to call with? A, and then B, and then C, and then D, right? So a bound method, because it's already got its arguments bound in. Usually count, you have to pass it a letter. Like hello.count will give you, well, a hello.count H will give you 1 because there's one H in hello. And hello count L gives you 2 because there are 2 L's. Well, it's going to count A's and then count B's and then count C's and then count D's. So it's going to order the string based on that and then look at the last one, right? So I is the most common letter in the doc string for dict. Right? So there's an example of it's a made-up example. I'm looking for a better one, but it's an example of what a bound method, what you can do with it, because it's a kind of partial, really, and we'll look at partials briefly later. But you've got this function, you want to call it with some arguments, and actually, I always know some of the arguments, and I want someone else to call it always with that argument. Well, instead of passing it, here, call this method always with this argument, and call this function always with that argument. With these ones predefined, what you do is you just do it. You create a partial, and a bound method is a kind of partial, a partial function, where you just say, well, here's the function, and it's already got those pieces bound together in a easy way. And this is just, if you walk through it slower, you'll see some of what's going on. I should probably right there. Ah, yes, I did it all there. And then take another 2-3 minutes and keep working on prefixure if you want. Okay, I'm going to move you along, maybe faster than you want. This is a good one to think about later if you want to sort of, again, cement your understanding of what, how you could hardwire these things, just so you really understand how it works. Should you ever hardwire these things? Probably not, right? Or hardwire, a monkey patch. There are reasons why you can do that in Python. I would want to, but leave that to library writers who are smarter than the rest of us, more experienced. Think about that more, or whatever. It's not just smarter, or not, maybe not even smarter. Sorry, I don't like the way people use smarter, including myself sometimes. Let me just skip past this. Okay, the type function for classes. It's all right. So great video, PyCon 2010 by Glyph turtles all the way down. The class statement is just a way to call a function, take the result, and put it into a namespace. So you knew most of that from what I told you before, except the part about calling a function. And that's what you didn't know, is that there's actually a function in Python that does this. It does the stuff of creating the class, right? It does this magic stuff. Well, the magic stuff is the function called type. We've seen it lots here where we pass it one argument, but if you look, it actually has two ways you can call it. You call it with one argument and it says, oh, I can tell you the type of that object. You call it with three arguments and you say, oh, you want me to create a new type with that name and those base classes and this dictionary of functionality, or functionality or values, right? So the dictionary is going to be all the stuff that's in the block, basically. All right, let's build a class. So there's my definite, just a regular old function. There's my def set double amount. I think I have a typo here. I do have a typo here. I meant to have the multiply by repeated from above instead of the dunder net. So I just created that and then I ignored it. This is the one. You can just cross that part out. This was used here and this piece here was used from earlier. So that is exactly what the class statement calls, is it calls type, kind of like that. Right? So remember back when I talked about the function, the def creates the name f in two places? Well, this is happening here too, right? Double number is a change to the namespace, but the class object itself also knows about the name, and when we call the type function directly without using the class statement, we have to pass it in ourselves. So that's why this shows up here. This is the superclass object, so it's just it's inheriting singly from object. And then here's the dictionary of things. And if I wanted to actually match this correctly, I would put that version in there too, the dunder version. Oh, sorry, I went backwards. But, okay. So now we can say num6 equals double number 3. And type of num6 is double number, and num6 class is double number, and it's got this ticked, and like all this looks familiar because it just built, it built a class for us. Okay. Obviously, the right way to do it is something like this, right? So, but there are people who write wonderful libraries for us, and those wonderful libraries do things with meta classes and dynamic classes created on the fly, and this is the way you can do those kind of things. So that all works as well. So
We're not getting the solution of prefixer here.
nope.
All right.
The dynamic called class, okay, we know that. However, when the class definitions are read, if meta class is defined, if there is a dunder meta class attribute in the class, then the object it references will be called instead of type. And meta class can be any callable which accepts the arguments the type does. That's how meta classes work. It's just like, it's basically a way to say, create this new class, but instead of calling type, which does the normal stuff, call my version of type that I have, or someone else's version of type, or whatever. Okay? And now, I think this is the last brain-bending one. Please go do the class statement exercise on bottom of page 21. And note that depending on whether you're running Python 2 or Python 3, you'll have slightly different syntax. Okay, let's look at least at the first part of this one. So the class statement is just a way to call a function, take the result, and put it into a namespace. All right? And that plus the fact that a meta class calls our function, whatever it refers to, instead of the type built-in function. So if I have a function called return1, which takes 3 parameters and returns the integer 1. You notice I called it name, bases, and attributes. Well, it could have been junk1, junk2, and junk3. Like, the names don't matter. The point is it needs 3 parameters because that's what type, just it's the same as type takes. So if I call return_1 with any 3 parameters, I always get the number 1 back. Now, I've got a lot of stuff in here. I should have cleared my namespace. So this in Python 2.7 or Python 3 something, it'll fail because I'm running 2.7. And there's the second part of that statement that didn't finish. Okay, so now I've lost it. Let me go back. Okay, so class X, subclass of object, metaclass. So what's going to happen is what's going to get passed to the return1 function. The name is going to be X. The bases is going to be object. And the attributes is going to be just metaclass. And then this function is going to get called, and that function, what it returns is what is going to be added to the local namespace, and what it returns is the number 1. So if we do that, we see that X is there and X is 1, and it's an int. Okay. So again, this is not like you're not learning metaclasses here. You're learning how you could create metaclasses and exactly what it means to create them. Right? Some other tutorial or book or reading is how you actually would do this useful things with this, but this is all that it is. This shows you just the simple bare bones of it in a kind of weird way. And then the second piece here, hang on just a second. So decorators are applied to functions. They can also be applied to classes. So in this case, return2 is a function that takes a class. It's in this case, it's going to take a class, and it's going to totally ignore it and just return the integer 2. So if I call it with none, it gets the number 2. And I see that there's, all right, so what does this do? So it's going to take this class, so same notion as function decorators. A decorator just takes whatever comes after it and returns something better, usually. In this case, it returns something not better. Maybe a little bit. I guess the integer 2 is a little bit better than a class that does nothing. But the point is what happens is class Y, this whole thing, this class gets created using the normal type, because we're not talking about metatypes anymore. Metaclasses, sorry, meta classes. So what is happening is this whole thing gets passed off to return2, and then Y is going to get stuck into the local namespace, not with the class object, but with the result of passing the class object off to the return2 function. So what Y is going to then have, there it is the integer 2. Okay? So two kind of odd misuses of class decorators and metaclasses that help you understand how simple it is what they actually do. The complexity comes in what you actually implement in these decorators and metaclass functions that replace what the type function does by default. Okay? Standard class methods. I want to give you a brief tour of standard class methods just to show you what they are. We're not going to go into any depth, and I've talked about some of them already. So you know about new. No, you don't. I mentioned new and init, and del gets called when an object goes away, which can either be happen when you use a del statement on it or when it gets garbage collected. Repr, str, and format, I'm not going to cover. These, get attribute, set attribute, get adder, del adder, get adder, set adder, del adder, and get attribute are all about attribute access. You can override what happens when an attribute is accessed. It's a little bit tricky to use these because inside them you can't use attribute access or it'll call itself. So you have to use other forms of the same, for get attribute you would typically call get adder inside it. A call is a very useful function, which if you define it on a class, then instances of the class can be called as though they're functions, and what gets run when you call them is that method in the class, using self, of course, the object itself as the first argument. These ones, you can override what these things do, and these are things like what the len function returns. Get item is what square brackets does. Missing is if something's not in there. Set item, del item, contains is what the in operator uses. Missing is used for some really, I've seen it used for some really interesting, when I was looking for a memoize example, there was a post on Stack Overflow talking about, using missing as a really fast memoize. Anyway, then there's a whole bunch of math stuff. And some more mostly math stuff. And then there's enter, exit, and next, which are for context managers. Sorry, enter and exit, which are for context managers. And then there's next and iter, which have to do with iterables. Okay? So that's all you get, just an overview. That's all the stuff that we've been sort of seeing but not really using, and you could use to go do interesting things. Well, I will give you a couple examples, though. Let me show you one. So get adder is a method that is called whenever an attribute is accessed, as opposed to get attribute, I think I've got this right, is one that's called when an attribute that doesn't exist is accessed. So what I'm going to do, what's going on here? Well, it says it's a class that returns uppercase values on uppercase attribute access. So if we try to access an attribute, it's going to see, first it's going to say if it's all uppercase and the lowercase name is in self.underdict, which is where the attributes are stored, then it's going to go look for the lowercase one and return it as uppercase. Otherwise, it's going to raise an attribute error because I want it to do what it should do. So d equals upper adder. It's got an empty dict. I add an attribute. The attribute is there. And here you can see the dict, self.dict. Now when I say d.foo, it's going to call this. It's going to go down there, and it's going to give me shoe. Kind of cool. And if I say d.foo.to, it's going to go down here and say, sorry, no such attribute. All right, let's talk about, I think this one, I'm going to skip for now. You are welcome to do it later because we're at 3:05 and there are a few more things I want to get through. I don't think we're going to quite finish, and that's common enough. The last few ones are neat examples you can try on your own, and I often don't get to them, but I put them in because sometimes I do. Properties. I do want to show you how properties work briefly. Very briefly, I'll just show you really quick. So what a property does is it lets you take attribute access and wrap functions in front of it, basically. And what you do here, for example, is it's just saying when we do a get, then return self._x. When we do a set, we set the value, and when we do a del, we del. So it's doing those things. The only thing I've done interesting in here other than just wrapping it, is to actually do some printing so we can see it work. And then the part you need to do is the x equals property, and then you pass it these functions and a description of the property. So these functions being these three methods. Okay, and there's an alternate syntax I'll show you. So here's how it works. P dot underscore x, there's nothing there. It's none because I set it to none. If I call P dot set x, well, of course that's going to work, and it sets it. And get x gets it, no surprise. But if I call P dot x equals foo, it also calls set x. And if I say P dot x get it, it's going to call get x. And if I delete it, it calls del. So the general rule in Python, especially if you're coming from Java where getters and setters are the rule, always write getters and setters, so much so that the IDEs will do them for you. Never do that in Python, because you can always change it later at the class level, and clients won't even know that it changed, right? And the way you would change it is just start with a regular attribute in class, instance variables or fields, and then later if you say, oh, I'd really like to control that better and maybe look at stuff coming or going and change it or store it in a different format, you can do it with these properties. And here's the alternate syntax, which uses at property, at x.setter, x.deleter, etc. And it works the same way. Okay, iterators. I apologize, I'm going to speed up a tiny bit, see if I can get through the big stuff. So how do iterators work in Python? The answer is a for loop. It evaluates an expression, right? Like for I in range 10. Well, range 10 would be the expression. That expression is the iterable. It calls the iter built-in function, and what the iter built-in function returns is an iterator. And that object's next method gets called over and over again until stop iteration is raised, at which time the for loop exits without throwing an exception. So what does the function iter do? Well, it checks to see if dunder iter exists as a method, and if it's so, it calls it. And it checks to see if it doesn't, then it goes and says, well, maybe it's a sequence, and I can figure out how to iterate over that, even if it hasn't defined a dunder iter method. I'll just go through it. Give me the 0th one, the first one, the second one, etc. And then eventually that is going to catch an index error when it runs off the end. It turns around and says, oh, I'll take that index error and return a stop iteration because that's what the for loop's looking for. That's how it works. All right, let's play with that a little bit. So there's an object, ABC, and if I call iter on it, it's of type list iterator, special kind of iterator, I guess. And I can look at it, and it's got a bunch of stuff, including a next method, which in Python 3 is dunder next. I think they got rid of next and added dunder next. I know they added dunder next. It has, as we saw, and I call next, I get the A, I call next, I get the B, I call next, I get the C, I call next, I get stop iteration. And very important if you implement these, if I call it again, I still get stop iteration. If you forget to always return stop iteration, if you assume it'll stop and not keep trying, then you'll have weird bugs. So make sure if you ever write your own iterator, which is pretty easy to do actually, that you always handle the case of multiple calls to next afterwards. Here's of course the way you use it, right? You just say for I and M, print I, right? Now behind the scenes, what was going on? Do you remember? This was going on, right? Because, well, actually I'm lying. I think list does have a dunder iter for efficiency reasons, but it wouldn't have to as a built-in. Conceptually, this is what's going on. If it's a sequence that doesn't have a dunder iter, it'll just use the get item and it'll still work. And then when it gets the index error, that turns around. I'll prove it to you. All right, here's a verbose list, which is basically list with a get item that prints when get item is called. So let's create one of those things. It just stores whatever I passed it into items. And then let's call next. Oh, can't do that because it doesn't exist. So let's make an iterator out of that iterable by calling the iter function. And now we've got an iterator object. And now we can call its next. And so it's going to call next. And what happens is called get item. And then it returned the A, B, C, stop iteration. So notice that get item was called. Get item raised an index error, but the wrapper that the iter function returned caught that index error, and instead raised a stop iteration, which is what the for loop's looking for, right? Which is why that just works without the weird exception at the end. Okay? I'm going to leave the exercises for you to do later and the optional exercises because I want to get through a little bit more in the next 9 minutes. Do I have that timing right? We finish at 4:40. Yes. Thank you. I'm glad I asked. So what did I skip earlier? The optional exercises. Now, is this a good time to go back to those optional exercises? Yeah, let's do that. Go ahead and go back to the optional exercises on standard class methods on page 23. I'll give you 2 back-to-back exercises. Sorry about that. So I'll give you a few minutes to do these and then we'll walk through them together. If you finish them early, you can go do the iterators exercises.
Skip section, just previous skipping is.
Yeah. It's not supposed to get printed. for this exercise. If you're done early, even if you're not done, get those open so you can remember to do them later. It's really, really helpful to get feedback, as I said before, both on the specific tutorial, like part of why this tutorial is as good as it is and not less good, regardless of how good you think it is. It's better now because of feedback I've gotten the last 2 times I've done it here at PyCon. So please return the favor to the future. So get that open. And then just generally how we do tutorials, feedback's really, really helpful. But go ahead and take another 2 minutes to work on the exercise.
I'm not sure quite what, I had this class, I don't know, a while back, that I redefined get adder on, and it would work, do what I want. In other words, when I wouldn't find the attribute, it would go through in the database and find it different. Anyways, but when I tried to run
If you've already taken the tutorial, it's taking you to the thank you for doing the tutorial, well, not the tutorial, the survey.
So if you did one this earlier,
Remembering you're thinking that you've already done the survey.
the first one is, whereas the second one should work. I wonder if that's the way that was defined. Okay. Okay. So is that true for both, or you don't know? But the first one for sure, it will only work if you haven't yet taken the survey. Didn't test that. Second one should work regardless. Okay, let me walk you through this exercise. No, not that exercise. This exercise, which I'm not going to skip. So I did a whole bunch of rework of the last 8 pages of this tutorial and got it down to about 5, which is why I have more time than I thought, and it's way better than it was. So special thanks to the people who sat through this Monday night and helped me think through a better way of doing this. Anyway, so all I'm doing here is I want to see what actually gets passed when we call get item in various places. So well, that's fairly straightforward. We just passed it an int of 1, int -1. Okay, slice. So that's what happens is Python actually creates a slice object when it sees a 0:3 and hands that slice off. And the slice object has 0, 3, none, so it's got some stuff in it. Sort of similar to range, right? Start, stop, and step. No surprise. No surprise, kind of an odd thing to do, but 0. Okay, so let's try some of that ourselves on a list. A, J, yeah, you've seen these probably. You may not have seen actually using the slice object directly to do this, but it works kind of the same way. Now, why would you ever want to use a slice object? Why not just do it the right way, the simple way? This is a lot more complicated, isn't it? Oh well. There's probably no good reason. Okay. Oh, hang on. So, at this point, I'm going to jump where this should jump, but doesn't. Uh-oh. That didn't work. What's going on? Okay, technical glitch. We are going to not do the change of plans as I had intended. We will instead let you go straight onto the optional exercises for iterators. No, the exercises for iterators. Middle of page 26, exercises for iterators. Please do that now, and I will go fix this glitch. Okay, let's walk through the iterators exercise here. I'll only point out the things I think would maybe have been surprising. So that would have been fairly straightforward, I think, as would have that. That's not surprising. This might have been. Right? right? So the iterator, when you create an iterator, it will iterate over what you've asked it to iterate over. In this case, a list, every time you iterate over list, it's going to start at 0, 1, 2, 3. Oh, in this case, right? It's going to go 0, 1, 2, index error on 3, and do the right thing. Reversed, on the other hand, it doesn't let you do it that way. I think reversed object actually has a next method that does it itself, and once it's exhausted, it's exhausted. All right, so what's going on there, and again, don't quote me on exactly why these are different. The point is that you have to be careful with iterators sometimes, that some of them, you can use them over and over again, but that's not, you're getting lucky when you can, in a sense. If you want to use an iterator multiple times, then you should create a new one. So it does, and so you're asking me why am I calling the iter function on it? Because I can. So you should be able to call iter function on an iterator, and it'll do something. So I'm not gonna answer I'm not gonna give you satisfaction with my answer because I don't know for sure what the answer is. I'm saying, look out. Here's a pothole. What's in that pothole, Daddy? I'm not sure. I've never looked deep enough inside. I'm going back to the analogy. I'm walking my 6-year-old. And then the iter tools module has a bunch of cool stuff that you should learn how to use. Okay. Let me now. Oh, it doesn't like that. There. So let me go back and show you the example I wanted to show you when I had that technical glitch, which is we looked at how to, what I said facetiously, by the way, in case you couldn't tell, why would you use slice instead of just using it straight? Well, here's why you might use slice instead of using it straight. And there's a...
Skipping all the generator stuff?
I'm skipping them temporarily.
Okay.
This hints at a solution. This is sort of a small subset of something that I wrote a few years back at work, where we needed to look at files and grab fields, and those fields we wanted to grab them without actually, always having these constants or ugly syntax. So what this does, class unpacker, it defines these 3 slices, and it uses getAttr so that if the attribute you're trying to get is in, oh, and by the way, you pointed out that earlier, I think I got getAttr versus getAttribute, the definitions backwards. So make sure you look those up before I always get them confused. One is called when you do attribute lookup. The other is called when you do attribute lookup and it can't find it. So what I'm doing here, though, is when we call the attribute, if the attribute is header, trailer, or middle, then it's going to go figure out which one to call and get that portion of the record, right? And so now I can have this unpacker, which is an object that I can call, look at its header attribute, and it will pull out the ABC for me. And I can look at its trailer attribute, it'll pull out the MNOP or whatever. And it pulls out these pieces. And here, this is not that powerful. What was powerful is we were generating, what we did is we had code like this that we would say, well, we want this type of unpacker or that type of unpacker, and we would go grab a definition file that would have fields in these files that had lines that were hundreds of characters long with all sorts of interesting field names. And once we basically tripled that amount of code, they all worked by using this kind of magic behind the scenes. And so then programmers, developers could start accessing fields in a fixed length file that were the fields that the documentation said they were, as opposed to, oh, offset number, right? They could just use the names that the way they were documented, which lets them think at a higher level of abstraction, which is always a good thing for programming. So yeah, that was skipping way ahead. And now I'm going to skip back. And I'm going to have you not do the page 26 exercises. I'm going to go to 27 for the generator section. And we'll just make it in the next 10 minutes, I think, to get through pretty much all this. I'm way happier with this last section, the last 5 pages than I was a week ago. So, generators. What are generators? Well, this is not a generator. This is a list comprehension. This, meaning square bracket to there, is a list comprehension. You might have seen that. And the result of that list comprehension, that's a bad name. The result of that list comprehension is a list. And if we instead do a generator expression, where we use round brackets or parentheses, we call them round brackets here in Canada, by the way, then you get back this generator object, which is of type generator. It has a next method, cool. So we can call its next. And it does things on the fly for us. That's kind of fun. And then it just does the usual iterator stuff. Here's another one. If we just pass it off to list, it's a fast way to get the values out of it, because the list has the for loop in there for us and collects it all together. You notice that? So that hints again at when is one exhausted and when not. So the nice thing about a function, and I'll show you, I'll hold that thought. I'll show it to you in a moment. This is the way you would usually call it, is in a for loop. You usually don't use .next unless you're writing something fancy. So here's a generator, which some of you may not have seen. A generator is a function that has a yield in it. In other words, when Python compiles this function, looks just like a function. The only thing different about this function is it has the keyword yield somewhere in it. When it sees that keyword yield, it says, oh, you don't really want a function, you want a generator. And it does something slightly different behind the scenes. I don't know exactly what. And when it sees a yield, usually what you do in a function is you get a bunch of stuff together and you return it all. In a generator, you get a little bit together and then you yield it back. And then the caller does some stuff, and then the caller says, give me the next one. And it says, oh, I'll do some more until I get to the next yield, either down or around a loop or whatever, or waiting for input or lots of things, right? So list 1, 2, 3. Didn't I just say it's not a regular function? That's because you have to call it, right? So when you call it, you get back a generator object, and that's a little bit confusing between generators and regular functions. And if we take that thing and save it, so let's call it again and get back another generator object, but let's save it with the name it, I can just call it.next, it.next, it.next. Did you see the control passing back and forth between list 1, 2, 3 and me, the caller? Yield, and then I went back and printed it. Yield, I called it again, right? So you've got 2 pieces of code running in parallel. Well, not at the same time, because they're on one CPU, but that's pretty cool. Generators are great. You should use them as much as you can. And you should go look at David Beasley's talk on generators from 2 or 3 years ago. His tutorial, I mean. And then it calls stop iteration as well. So those of you who haven't seen much with generators, tell me which of the, oh no, hang on. Here's an example of a loop. And we get this thing we call next, yield 0, yielding 2, done, loop, falling out, stop iteration came back. So the generator, Python takes care of the fact that when there's a yield, when it falls off the end, stop iteration gets raised for you. And here's how you would usually see it run. A generator is a type of iterator. A generator is a function that instead of returning all its results at the end, wherever you've chosen n to be based on where you put the return, is it can just return it a bit by bit, and it sort of puts the execution on hold and then goes back to going again. We can chat more after. And again, here's how you would often see it, a simpler way. Okay. That was generators. Okay, and I did have that example. So I got ahead of myself with my comment where I said, those of you who have not seen generators much, which of these looks simpler? Easier to read, easier to understand? Yes? Yes. Examples of where you wouldn't want to compute something all at once?
Yeah, it'll basically save you in memory and stuff.
Save you memory, right? What else?
You're waiting for input from another source.
Right, and the third? Infinite list, right. Please generate for me all the Fibonacci numbers. You can write that as a generator, and it's nice and clean, and then you only call it as many times as you want, as opposed to create them all for me, right? It doesn't work. So those are the three. There may be other cases, but those are the three big ones I can think of where is why you would use it. So when you look at these, which one looks simpler? I think the first one. It's certainly shorter. What's the disadvantage to the first one? Yeah, you can't go backwards. Sort of like remember when we did iter 2, IT2, those ones, and I said sometimes iterators exhausted not. If you do this one, as you consume it one by one, you can't back up, you can't consume it again, because to do that you need to put it in memory, which is what the second one does. So I mean, this is really powerful, not just in terms of lazy evaluation is powerful in terms of saving memory and all those other cases, but it also can make the code really easy in terms of splitting up the computation. And that's where that talk by David Beasley is pretty cool. So you can see the way you call them is very much the same. And here I just called it putting into a list comprehension. Here's a quick example of a handy generator. Like you've got a file and it's split into paragraphs, and the paragraphs have sentences and the sentences have words. Well, that's the thing where you write something that does all that and returns words or sets of 3 words or something like that. It's really painful. You break it into a few generators, one that returns the paragraph, one that returns the sentences, with something kind of like this, maybe simpler, and it's way easier to understand. So here's an example where if you look at the file, right, it's just going through, collecting things until it finds a blank line, then it returns it, and then it goes back around and collects until the next, keeps collecting until it finds a blank line, returns it, keeps collecting until it finds a blank line, returns it. When it's all done, it gives you the leftover. All right, so here's what the file looks like. And if I open that thing and pass it off to paragraphs, turn into a list, it's going to be just those 3 paragraphs. And you can see them, right? It's got the, after the paragraphs, it's got there's the first paragraph, and there's the second paragraph, and there's the third paragraph. And there's the talk I told you to look up. Okay. Oh. No, it's not right in time because I have one more thing I want to show you, which is, it's just a fun example I love giving because a few people it's like, oh, I get it. So we've talked, I won't explain, I'll just show it to you. Suppose many of you, I'll be done in 3 minutes. Many of you are used to thinking about things a certain way because you've programmed in another language for a long time. And you've been trained not to think of a whole bunch of solutions. Without knowing it, you were trained to only do things a certain way. Here's an example of where first-class objects, you can get a different kind of solution that I find useful enough to keep you over 2 minutes. I want to create a calculator program, little calculator function that can handle only single digits and single operators. So it's kind of simple because I want to get it done in 2 minutes. So 7 plus 3 is 10. We knew that. Did you know that there's an operator module that exposes all these things as names of objects, which are function calls and such. So I can call operator.add with 7 and 3. If I take this expression and I can split it using tuple assignment, tuple unpacking assignment, assignment of those things combined, I can just do that and I'll get 7 plus and 3 as the left-hand side operator and right-hand side. So I get 7 plus and 3. Let's turn 2 of those into ints. So I get not 3 strings, but 2 ints in a string, literals. All right, so now I've got those 3. And now let's turn them around into plus 7 and 3 to make it look a lot more like that. Now I can do operator.add and the pièce de résistance. I create a dictionary of operators and say, when you see a plus, I want you to call this. When you see a minus, I want you to call that. So now I can say that, and I get the 10. So when it sees plus, it goes, looks up plus, gets this back as a function, calls the function with those 2 operands, those 2 parameters. Throw it in a function, combining all that stuff I just did. Ta-da! Ta-da! Not going to work. So now what do I have to do? Well, I have to go back to my big if then else statement that I created over the years and add another if at the end, right? I have to do more boilerplate code. No, I don't. I just do that and I am done. Right? So there's an example of the things look for when you're learning doing Python. Look for ways where, oh, I don't have to do it the way I always used to think I had to do it. There are other ways, especially a lot of them having to do with data structures, first-class objects like functions that you can store in dictionaries, etc. And yeah, that's an interesting question. So I didn't show you the last example. I think I skipped a couple exercises, but that is the end of our time. And I'm going to remind you to do the survey. Pardon? Oh, it got fixed. Interesting. Who changed something? In? Cool. Excellent. Got it. So I get it. Yeah, didn't test that yesterday when I was cleaning that up. Okay, so thanks everyone for coming. I got, feel free to ask me questions. You've got my, I think my email was in the sheet. And see you around at Python. Have a great rest of the conference.